Hello, my people. Okay, in the first video on alternating series, we basically talked about convergence and divergence of those series, and it was a pretty easy test to use. There were simply two criteria that we had to use. One was that each successive term, which analytically looks like b sub n plus 1, needs to be less than the preceding term, or equal to, and the b sub n, as n goes to infinity, needs to go to 0. And if those two things are satisfied, then we have a convergent series. Well, once we start talking about convergent alternating series and the fact that they're sums, then the question arises, okay, well, what is the sum? Like, what does it all add up to? And sometimes you can actually get an accurate sum, and sometimes you have to basically settle for an approximation. Now, the approximation, of course, if you have an infinite number of terms, the approximation is what is known as a partial sum, okay? And the partial sum is exactly what it sounds like. A partial sum is a sum of part of the series. Like basically, if it's an infinite series, then you would designate maybe the first 100 terms is S sub 100. And S sub 100 would simply stand in for the sum of the first 100 terms. Now, of course, there is, let me put it this way, okay. Let's back up for just a quick second, just make sure that we're on the same page before we move forward. If I have a series, and that series has a sum that we'll call S, and it is, n is equal to 1 to infinity of a sub n, and it's, a sub 1 and a sub 2 and a sub 3 and a sub 4 and all the way out. Then basically, a partial sum is we'll basically rebrand this as I to n. A sub I becomes a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus dot 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 plus a sub n. Okay, like I said before, this right here is what is known as a partial sum. Now, if you're wanting to know how good that partial sum is, then basically you need to figure out what the remainder is. And the difference, between the actual sum and the partial sum is that remainder, right? So basically your R sub n is going to be the sum minus the partial sum, okay? And of course, what that means is basically, try not to run into this, but if basically it's this minus this, then you're subtracting the first through the nth term from this original. So what you have is that n plus 1th term, or n plus first term, and then on out to infinity, okay? So that helps us make sense out of some of the notation here in this little box, okay? And that little box basically says the alternating series estimation theorem. If S is equal to sigma -1 to the n minus 1 of b sub n is the sum of an alternating series that satisfies those two conditions, which basically is another way of saying you're only going to be able to find an estimation and a partial sum for a convergent series, right? That's all that means. So this just means that you're talking about a convergent series. Then what you need to know is that R sub n, and R sub n of course can be negative because these things do go back and forth between positive and negative. The magnitude of the remainder, which is equal to the difference between the sum and the partial sum, is simply less than or equal to the next term. That's it. So if you're basically getting a partial sum to the nth term, the next term, b sub n plus 1, is your maximum error. And if we think about it, that makes sense based upon the visual proof that we saw earlier, right? So if we have S, and S is the actual sum that these, constantly decreasing addition and subtraction actually is leading towards, right? B1 minus B2 plus B3 minus B4. It's basically cycling in towards some definitive value S, right? Well, if each successive term has no way of going beyond the previous term on the number line, then basically the error in here cannot be more than that. And therefore, is it probably at times a lot less than the next term? Yes, but logically it can't be more than the next term. And that's all you're doing. You're basically finding a way of basically being logically certain for a maximum error. And in an alternating series, the maximum error is simply the next term. Okay. Now, here's what that means in brass tacks. Okay. So, because you're going back and forth from here, you recognize the fact that S sub 1, the first partial sum, is going to be an overestimate, right? Because I'm to the right. I'm more positive than the actual sum. Well, B sub 2 will be less than. B sub 3 will be more than, an overestimate. B sub 4 will be an underestimate. Overestimate, underestimate, and on and on and on and on and on. And of course, it's real simple. The way that you deal with that is if the final term is positive, then the partial sum is an overestimate. If the final term is negative, the partial sum is an underestimate. So, if we're given that we need to find the 50th partial sum, S sub 50, of the alternating series, and it is is the 50th partial sum an overestimate or an underestimate of the total sum? And for that, you simply need to plug in 50, right? If you plug in 50, you recognize that you're going to get negative 1 to the 50 minus 1 over 50. So you're going to get negative 1 over 50. Now, that means that the final term is negative, and therefore it is an underestimate. Okay? Now, let's go ahead. Let's figure out what that actually is. Okay? Now, we know that we have, let me go ahead and put this up here. All right, there we go. Alrighty, so our basically alpha F2 scroll down menu gives a summation at number 2. So you can basically plug in 2, and you have, let's go x from 1 to 50, right? And then we simply need to plug in what that is right there. X minus 1 over x. And you can do it for n or whatever. I'm just doing it for x because when I use this variable button right here, that's what it's giving me. And that's going to sum up the first 50 terms. Okay. Now, if you were to do the first 51 terms, you would simply need to go back here. Right, and press enter. And notice that that's larger, right? Because this last term of the 50th partial sum took us in a negative direction, and the next term would take us in a positive direction, okay? Now the actual error is going to be the 51st term. So if you were looking for the actual max error, right, it would be equal to 1 over 51. It would be the absolute value of the next term. All right. Let's consider this example right here. First of all, it asks us to show that the series is convergent. So we're going to go back to the stuff from last last video and determine its convergence. Now remember, I need to determine that b sub n plus 1 is less than or equal to b sub n. Now b sub n plus 1 is 1 over n plus 1 and 5 to the n plus 1, and that I need to basically relate to n times 5 to the n. Now, n plus 1, both as a factor and as an exponent, they both make this denominator larger. When you make the denominator larger, you make the quantity less than. You make it smaller, okay? So that first condition is satisfied. The second condition is I need the limit as n approaches infinity of b sub n to be equal to 0. So what that looks like for this particular series is 1 over n times 5 to the n. And if I'm going to go ahead and do this, like a big bad calculus student and use my proper limits at infinity, it's probably a good idea to go ahead and pull these apart. And both independently, they satisfy the fact that this is 0 times 0 or 0. So check. It is convergent. Okay, we've checked, and both of the conditions check out. Now, how many terms of the series do we need to add in order to find the sum to the indicated accuracy? So, if we have the accuracy, meaning the max error given to us ahead of time, what we're looking for is the first term that is smaller than that, and that first term that's smaller than that will be that quote-unquote next term, and it is the first term that is beyond the partial sum. So let's just go ahead and sort of let's just go ahead and start listing out some of these, okay? And I'm going to go ahead and include, although you don't really necessarily have to, I'm going to include the negative 1. So I'm going to make this alternating rather than just doing the sum for the b sub n, right? Without the negative 1 to the n. So this winds up being, well, if you plug in 1, this is going to be the first one's going to be negative, right? And it's negative n times 5 to the n plus 1 over 2 times 5 to the 2 minus 1 over 3 times 5 to the third plus 1 over 4 times 5 to the fourth, and then minus 1 over 5 times 5 to the fifth. Now let's go ahead and let's actually look at some of those. Now this denominator right here is 5. This denominator right here is going to be 50. This denominator right here, now 5 cubed is 125, and 125 times 3 is 375. I'm getting closer, right? Because if the error right here is 0.00001, that of course is another way of writing 1 over 10 to the fourth or 1 over 10,000. I'm looking for the first term that has a denominator larger than 10,000. And this is in the hundreds, but it's getting closer. Now 5 to the fourth is 625, okay? And I'm going to multiply that by 4, and that's going to give me, that's going to give me 2,500, right? This one right here, I'm guessing, is going to give me one that is larger. So that actually winds up being 5 to the sixth, and that gives me 15,625. That means that right there is my next term, and if that's my next term, then this is my partial sum. And my partial sum is going to be S sub 4, the sum of the first 4, okay? And of course we could find out what that sum is if we so choose, right? We can go ahead and okay, so let's go ahead and alpha F2. That gives us the summation formula right here, and we'll just use X since it's easier on the home screen, since we're not in a different mode right now, and it'll take time to do that. So what we're going to do is negative 1 raised to the x, and then I'm going to do a fraction of x times 5 to the x. Okay, and it gives me negative 1,367 over 7,500. But if I wanted a decimal approximation, I do the alpha F1 press 4, and that's my fraction to decimal conversion operation, and it gives me it is equal to negative 0.182. That is what the partial sum adds up to, and that partial sum is within 1/10,000th of being the actual sum, which, you know, is a pretty good approximation, right? Okay, let's go ahead and let's do the next one. And this is actually the last example. This section is not overly robust in terms of its conceptual ask of the student, so I'm not gonna ask you to spin your wheels and watch a bazillion examples when 2 or 3 will do. Okay. Now it says approximate the sum of the series correct to 4 decimal places. Now correct to 4 decimal places is exactly the same error that we were talking about in the last one. And so they're just basically, that's another way of saying we want the error to be less than 1 over 10 to the 4th. Okay. So let's go ahead and let's do again what we did in the last one. If we're working backwards to the error, to the number of terms, because if you're given the number of terms, it's easy to find the error. This is being given the error and being asked to work backwards to the number of terms. Now remember, in order to find an error that is less than 1/10,000th, I need to find the first term that has a value, an absolute value, a magnitude of less than 1/10,000th. And that less than 1/10,000th will be the max error. That term will be the quote-unquote next term, and it will be the n plus 1th term, and basically the n number of terms before that comprise the partial sum, which actually has that error to it. So we're just going to go ahead and start listing off some of these numbers. That's negative 1 to the nth over 3 to the nth and n factorial. And so the first term is obviously negative, and so we're going to go negative 3 to the first times 1 factorial, right, plus 1 over 3 squared times 2 factorial, 1 over 3 cubed times 3 factorial, 1 over 3 to the 4th times 4 factorial, minus 1 over 3 to the 5th times 5 factorial, right? Okay, well, 3 to the first and 1 factorial, that denominator is going to be 3. 3 squared and 2 factorial, that's 9 and 2, and that's going to be 18. 3 to the third times 3 factorial, that's going to be 27 and 6. So 27 and 6 winds up being 162. And 3 to the 4th and 4 factorial, that's where your arithmetic gets a little bit, your mental arithmetic gets a little bit taxed. But 3 to the 4th is, of course, 81. And 4 factorial is going to be 24. So that's 81 and 24. You could do that in your head, but I'll spoil the surprise for you. It's 1944. Now that is almost 2,000. And look, by order of magnitude, that's gotten much larger over just 4 terms. I'm assuming that this next one is going to be my last term. And basically that has a denominator of 29,160. That is going to be, basically that denominator is larger than 10 to the 4th. Therefore, the value of that term is less than 1 over 10 to the 4th. That means that this right here is my error, okay, which makes it also my next term, right? And I keep saying next term because if that's my next term, then my partial sum is everything that precedes it, okay? And that partial sum is going to be s to the 4th. Now, we can go ahead and just do that longhand if you wanted to. You could go ahead and clear that off and go, okay, well, I want negative 1/3 plus 1/18 minus 1 over 162, and then 1 over 1944, Or, in that case, it's negative 551 over 1944. How's that for a common denominator? Lovely, right? We could, however, do x to 1 to the 4th and just sum up the first 4 terms of negative 1 to the nth, or in this case to the x, and then 3 to the x times 3, and then factorial is also under this math right here. You have to go over the number though. Or is it probability? I think it's probability. Yeah, it's probability. There it is, number 4. And then you go 4th, okay. And so that is, we double check, make sure that that is exactly what we have in terms of what we have here, and it is. And we press enter, and our number is negative 10 over 243. Now that probably doesn't. Where did I go wrong? Oh, yeah, it's because, and that's a good thing that I double checked. That is not actually what I need. What I need is x to the factorial, right? And that is the correct answer, okay? So it doesn't hurt to do things both ways, okay? And so I know that my s sub 4 is equal to, n is equal to 1 to 4 of negative 1 to the nth, 3 to the nth times n factorial, and it is equal to negative 551 over 1944. And of course we can do the, finding the fraction from it, and it winds up negative 0.283. That is the sum, that is the partial sum, the approximation of that infinite series, and we know that it is correct to 4 decimal places. Not that I showed 4 decimal places, but that brings us to the end of the videos on alternating series. I hope that that was clear. If you have any questions, please do email me. Bye.